It's a pleasure to introduce our friendly neighborhood Marta Pedroni, which is a PhD student in Geneva and also here at USI, under the supervision of Chris Buttrich, and she's also part of the SNF project Beyond Standard Physics. Marta, the floor is yours.
Thanks. Thank you for being here, and thanks now for sharing the talk, and also for all the people online following the talk. So today I'm going to talk about the singular case of space-time singularities in quantum gravity. I will start with the general, but not too general introduction. So I was not sure about the background of any people in this room. So I was like, okay, maybe I'm gonna take the things very slow, but then I will not have time to talk about other stuff. So I will try to get it as slow as possible. Then I will talk about singularity in quantum gravity. I will present a new hope for singularity, and I will discuss whether or not singular spacetimes emerge. But we'll see more about the structure later on. So let's begin with the introduction. So GR is famously described by this quote of Wheeler: matter tells spacetime how to curve, spacetime tells matter how to move. The idea is that there is this four-dimensional entity, spacetime, which is curved by matter, and at the same time matter moves in spacetime accordingly to how the spacetime is curved. So there is this interaction between matter and spacetime in GR, which is one of the main features of the theory. I guess I don't have to further define spacetime for now. You all have an idea of what GI says also from, I guess, sci-fi movies and this kind of stuff. So what about quantum gravity? That's not very sci-fi topic yet. The idea is that there are different research programs aiming at elaborating a quantum theory of gravity. So a theory that could actually conciliate relativistic physics and quantum physics. What's the matter? Well, we know basically that GR is false. So it's a very good theory. It's one of our best theory in physics now, but it doesn't take into account the quantum nature of matter. So matter plays a very important role in the theory, but we know that matter is quantum from quantum theory, and GR is a classical theory, so it treats matter classically. So we need to find a theory that actually can bring together these two aspects. So a theory of gravity that actually is able to treat matter as quantum. And that's why we are looking for a theory of quantum gravity. And as for now, we have different research programs. So we have different theories, but we don't have yet a definitive theory. So it's not, we don't have an established theory. We have many good theories, like string theories, loop quantum gravity, causal set theory, but there is not yet like final theory on quantum gravity. So when I will talk about, when I say like doing this in quantum gravity, it just means like in the different research programs in quantum gravity. And usually it refers to something that's kind of common to the main research program. So we expect that a final theory of quantum gravity will have this kind of feature. So space-time singularities, which is the main topic of this talk. Just a very intuitive idea of singularity. I guess you all know more or less what we're talking about when we say space-time singularity. The one classical idea that we always have is the Big Bang singularity. So the singularity at the beginning of the universe, the initial singularity. Another famous singularity is the black hole singularity. So the idea that inside the black hole there is a singularity. Naive characterization is then something that has to do with infinity. So usually we say that singularities are points at which some physical quantity, so like density or the curvature usually, goes to infinity. Another intuitive idea is that of missing points in space-time. So there's space-time, and then it's singular at some point, like inside the black hole, or like at the Big Bang. And that's kind of intuitive idea we have of singularities. And in GR, people are not, so we have this kind of singularity in GR, and in GR people are really not very happy about singularities. So there is this general idea that nature abhors singularity. So there is a famous quote by Bergman, say that GI contains the seeds of its own destruction because it contains singularity. And also there are, in general, like physicists, they're really against the idea that there are infinities in nature. So we just saw that singularities are somehow related to infinities. And the idea that infinities are just like something in mathematics. It's not really, we cannot have infinities in nature. But in general relativity, we have the singularity theory. So it has been proved, mathematically proved, that singularities are unavoidable in general relativity under some critically reasonable conditions. Again, like there was a big debate about singularities back in the 50s and 60s, especially, and in the 50s, there was this idea that singularities were just a mathematical artifact due to some symmetries. So when, for example, in the black hole, when stars were collapsing, I mean, we had in mathematics that we had a singularity just because we're taking like a collapse to be very symmetric and things like this. But in real life, it was not like this. But then in the 60s, Penrose put forward the first singularity theorem, showing that actually, independently of the symmetries that you take in the collapse, or how the stars collapse, if it does collapse like as the star does in the black hole, you have a singularity according to the mathematical for the topological structure and so on. So it seems like physicists are not very happy about singularities, but they cannot actually get rid of singularity in general relativity. So the issue is what kind of entities are these space-time singularities? And there are people that still like want to claim that they are just mathematical pathologies. But other people say, okay, we have singularities as a prediction of general relativity. So why shouldn't they just be something out there in the world? So why singularity cannot be some physical entity? So this is the debate in GR already. And I want to see like how this debate kind of develop in quantum gravity. So in light of some results that we have in quantum gravity. So what is this talk about? Let's get serious. So the idea is that in quantum gravity, you have this singularity resolution. So singularities will disappear in quantum gravity. So again, in a final theory of quantum gravity. And this seems to actually support the idea that singularities are merely mathematical pathologies from GR. However, if space-time emerges in quantum gravity, so it might be singular structure. I will argue in this talk that, the first thing I will actually show how, so I will actually try to provide an argument for the first point. So I will say like, okay, this is this general idea, let's try to put it in a rigorous way. Then I will say, okay, maybe there is this way out, this kind of new hope for singularity. And then I will actually argue against this possibility. So singularities in quantum gravity. Why we should think that there is a singularity resolution actually? Well, there are at least two good reasons to assume singularity resolution. The first one is in analogy with other physical theories that we already know. So other, let's say, case studies that we have. So for example, in the various classical theories that we see that the singularities disappear upon quantization. And there is the example of electrodynamics. So in classical electrodynamics, there's some kind of point particle singularities, or the example of the hydrogen atom. So the collapse of the electron collapsing onto the nucleus in the hydrogen atom. But then if we look at quantum electrodynamics, these kind of similarities are just vanishing. The second and more compelling reason is that we have several works in physics, in quantum gravity, showing how singularity resolution is successfully obtained. And this is a robust result. So we have like these kind of results appears in different theories of quantum gravity and in also many different models. So an example is the singularity resolution in loop quantum cosmology. So loop quantum cosmology, well, in order to explain loop quantum cosmology, I have to talk a bit about loop quantum gravity, which is one of the main research programs in quantum gravity. And the idea of loop quantum gravity is to take relativistic spacetime and quantize the spacetime, well, with a certain quantization procedure and so on and so forth. The important bit is that the fundamental structure that we have display a discrete geometry. So, for example, well, I mean, the fundamental entities of the theory are these spin networks and spin forms, and we have some operators for area and volumes, and these operators are they have discrete values, they have a discrete spectrum. Loop quantum cosmology is a symmetry reduced version of loop quantum gravity. What does it mean? It means that for like simplifying things and for actually having some sort of results in the dynamics of the theory, they just take the simplified models. So some simplified models, in particular, models are like homogeneous and isotropics. So this kind of the cosmological set. So this, I mean, this usually what is done in cosmology. So the kind of models that we have in cosmology are isotropic and homogeneous modeling most of the time. And then loop quantum cosmology is said to actually cover the cosmological set of the full theory. Well, so which kind of singularity will loop quantum cosmology solve? Well, the cosmological singularity, so in particular the Big Bang singularity. And the result are these bouncing models. So let's see how it works. The idea is that the singularity is avoided thanks to the discreteness of the quantum geometry. And so with physical observables, so the quantity that we measure, are represented by bounded operators. I mean, I said before that also like in loop quantum gravity, the expectation values of this operator remain finite. And in loop quantum cosmology, this translates to the fact that they remain finite even when the classical operator, the classical value diverges. So this means that the classical equation has to be modified. And instead of the classical evolution that we have a quantum evolution in which there is an effective repulsive force when we get to values close to the Planck scale. So instead of having the operators becoming singular, the operators remain finite, and what we have is this effective repulsive force, which basically makes the universe expand again. So the idea is that the singularity is replaced by bounds. And throughout all the evolution, we don't have any point in which the theory becomes singular. So it remains like we have a non-singular description. And this is a masterpiece. Well, I mean, like I did the blue. to exactly to replace the explosion is supposed to be the Big Bang with the blue rendering. It means like some kind of non-singular, non-spatiotemporal description provided by the theory of quantum gravity. And I hope this helps to get the idea. So what's the folklore that we have in physics, among physicists about singularities in quantum gravity? And the idea is that singularities are not physical entities. We have already seen that in GR, physicists are not very friendly with singularities. In quantum gravity, we have the idea that they disappear. So the singularity resolution seems to support that the space-time singularity are only mathematical pathologies of general relativity. So this is the generality. Let's try to get a clear argument from this line of reasoning. So the first premise is the assumption of singularity resolution. The second one is that if space-time singularity are avoided in quantum gravity, then they do not exist fundamentally. By modus ponens, we have that space-time singularity do not exist fundamentally. But then if space-time singularities do not exist fundamentally, they're just mathematical pathology of GR. And then we get to our conclusion. Now, the question is this argument sound? The first is just our main assumption. So throughout all the talk, our working hypothesis is that there is actually space-time singularity resolution. The third one is obtained by bonus ponens, so the focus is on the second and the fourth. So the justification for the second seems to be quite, I would say, uncontroversial, but let's see. So the idea is that if a more fundamental theory avoids the singularities in the less fundamental theory, then the singularity do not exist fundamentally. And the idea is that quantum gravity is more fundamental than GR. So if space-time singularities are avoided in quantum gravity, then space-time singularities do not exist fundamentally. But what about the fourth premise? So the fact that if space-time singularities do not exist fundamentally, then they are just mathematical pathologies of GR. Is this justifiable? Well, the point against these premise is that space-time singularities might be emergent. So this seems to give a new hope for supporters of singularities. Let's see exactly how one can put forward these views. So how should we articulate this new hope? In order to do so, we should first clarify two important points. So the first one is definition of space-time singularities. So we saw before an intuitive idea, intuiting class of singularities. We all have a kind of more or less clear idea of what space-time singularity is, but let's see what the, let's say, standard definition tell us about singularity. The second point is space-time emergence in quantum gravity. So it's actually very difficult to provide a good definition of space-time singularities. And there is, there are many good papers, in particular this one, that shows, actually all the struggles that one have to get to a good definition. And even the definition we're gonna take into consideration is good enough and is a standard definition, but it's still not totally uncontroversial, I would say, or it's not totally satisfying. But the main problem, and also like I think the source of the whole, let's say, the source of all the difficulties we talking about the nature of space-time singularities, whether they, I mean, what kind of entity they are, is also the inclination of treating singularities as things. So actually, space-time singularities are not localizable things, and they are not point of space-time by definition. So singularity is not a point of space-time. There is no point in space-time or space-time at which space-time is singular. And the idea is that singularity in like any other kind of field can be localized because the field is in space-time. So we can say like, oh, this field is singular at this point. But space-time itself, as a field, has nowhere to be singular because there is no, let's say, space-time itself should be in theory the field containing the location of things and so on. But if we have a point at which the space-time breaks down or whatever, it cannot be a point of the space-time or in space-time. So the standard definition is given in terms of geodesic incompleteness. A geodesic is the shortest path in space-time. So, well, I mean, we have geodesic in general on curved space. For example, even the one famous example of geodesic are the one on Earth, for example. And the idea is that it's the correspondence of a straight line, but on curved space. So definition of singular spacetime is the following. A spacetime is singular if and only if it is geodesically incomplete, which means if and only if it contains a maximally extended timeline for null geodesics that terminates after a finite lapse of replica. What does it mean? Okay, I have explained what the geodesic is. Geodesic in spacetime, you can think about the shortest path that one can take to move in spacetime from one point to the other. And a timeline for no geodesic means like, well, the path that timeline for any object take, the worded line is also called. And null is the one of light. And the idea is that if you could extend, like you cannot extend this path infinitely. So it will come to an end, well, unexpected. And it's not because of the, so it's not because of the geometry of space or whatever, but it's because something happened. And the idea that this something happened is, well, the space-time is singular. Okay. So there are two important remarks to make. The first one is that there is a shift from talking about singularities to talking about singular space-time. So the definition that we have, our best definition of singularity is actually a definition of singular space-time. So what is like for a space-time to be singular. And another important remark is that this property is, so the fact that the space-time is geodesically incomplete is determined globally. So it is a global property of space-times. We'll see after how these how this matter in the debate. Let's get to the second point of the formulation of this new open singularity. Space-time emergence. Well, if you read paper in philosophy of quantum gravity, for sure, I can almost bet that you will find some points, some mention, if not, it's really the main focus, but some mention to space-time emergence. And the idea is that space-time does not exist fundamentally. So the fundamental structure described by quantum gravity is non-spatiotemporal, but still space-time emerges from the fundamental, from this underlying structure. And well, we'll see after a bit more on actually emergence and how this can be, how this is treated in the literature, let's say. But the general grasp is this one. So space-time does not exist fundamentally, but it exists derivatively. So this new hope, this points to actually the Fourier experience is false, is to argue that singularity can be an emergent property. So if space-time emerges, then singular spacetimes might emerge as well. So it's not true that space-time singularities do not exist, or they're mathematical pathologies, but there is a way in which the status of singularities is restored in the same sense in which that of space-time is. But is it really the case? So can we actually say that singular spacetimes emerge? I will now provide 3 arguments against this idea. And the 3 arguments are based on, well, ways in which we have space-time emergence in the, well, ways in which space-time might emerge, let's say, or position of space-time emergence that we have in the literature. So the first argument is the argument from space-time eliminativism. And let me point out an important clarification. So now I want to draw a difference between space-time as physical entities and space-time as mathematical entities. And the idea is that space-time as a physical entity is the object of, let's say, ontological emergence, when we're talking about space-time emergence in quantum gravity. And it's what is supposed to be part of our ontology. The mathematical entity is the mathematical structure described by the theory by GR. So space-time eliminativism claims that space-time as a physical entity does not exist, and the idea is that it does not emerge from the fundamental spatiotemporal structure. This idea has been defined by Baron in a couple of papers, like this one. It's not super popular, I would say, in the quantum gravity, philosophy quantum gravity community. But still, like Sam Baron is in this paper defend the idea, say that it's still like a possibility. And it is that if it's what it's really nice to be actually, if it's like, if this possibility is right, then the hope of restoring singularities quickly sinks, because if singularities have the same status of space-time in quantum gravity, then space-time does not exist, so singularity cannot exist as well. Or, well, singular space-time do not emerge. The second argument is taking stance in another idea of space-time emergence, and it is that space-time emerges only in the domain in which GR applies. And I would say is like kind of standard claim in philosophy of quantum gravity. But why? Well, because we have many models in quantum gravity. They are not fully no spatial temporal, so there is no way to recover space-time in these models, and also like some domains. So, for example, in the case of loop quantum cosmology, the example we saw before, the idea is that space-time is recovered. Well, you saw the picture. So on the two ends of the picture, but the middle, the nice drawing I did, is still like in a spatial temporal state, or something that is not doesn't correspond to an emergent space-time. So the fundamental degrees of freedom do not always give rise to space-time. And singularity resolution shows that the singular structure is not recovered. So what we have in quantum gravity is different prediction with respect to GR. While GR predicts a singularity, quantum gravity gives us a non-singular description. So it seems like space-time should emerge in this domain close to singularities. But this sounds weird, because there is a tension between this intuitive idea and the expectation that space-time emerges with this property. And we saw before that actually being singular is a global property of space-time. So how can space-time emerges, and is singular structure? Well, the property of being singular does not. Well, the last argument, I hope gives a definite answer to this problem. And the idea is that we apply space-time functionalism. So, well, in the case of space-time emergence. So only the features of space-time of the physical entity functionally relevant in producing empirical evidence emerge by having the functional role fulfilled by the fundamental structure, basically, by the entities in the fundamental structure. And it works exactly how functionalism generally works, let's say. That's the basic idea. So there is this two-step process. First, we specify the functional role of this feature. So we functionalize spacetime. And then we have to show how the entities fill this functional role. So how this functional role is realized in the fundamental structure. To clarify a bit out, even though I'm not an expert in functionalism, the classical example that is given in functionalism is the one of pain. So the idea is that the functional role of pain is taken to be something like, I don't know, a causal reaction, or some kind of mental state sometimes, or some input-output thing. And then he said that this functional role is realized by the C fiber, which are some fiber in our body. And then this how pain is functionalized, basically. So pain is functionally emerged from the C fiber because its functional role is fulfilled by this thing. And the same idea should apply here. So why cannot being singular functionally emerge in this way? So why we cannot apply space-time functionalism to singular space-time in the on the singular part? And the idea is that this property does not have any functional relevant space-time role. I mean, the idea is that functional relevant should produce empirical evidence, and singularities do not, I mean, by definition, are not observable. They're not in space-time. They're not off spacetime. They're like directly spacetime, but it's not. I mean, they cannot be observed. And in any case, in light of singularity resolution, there will be nothing in the fundamental theory that could fulfill this role. Because we saw that what we have in the fundamental theory is something like different and gives different prediction. So the reasonable conclusion seems to be that the property that we have, this property of being singular, is property of spacetime, like the mathematical entity, but not spacetime, the physical entity. So it's not the what emerged in quantum gravity. Conclude, I think I'm perfectly on time. What I did or tried to do in this talk is to improve on the standard view. So the view that singularities are just mathematical pathologies of GR in light of singularity resolution. And I structure the folklore in a precise argument. I consider a way out of the argument. So the idea of singularity might be emergent. And then I provided 3 arguments to show that this way out turned out to be a dead end at the end. So the idea is that still singularities, well, singular structure is not physical. And I guess at the end of the day, I agree with physicists on this, but I think like still their way of putting forward the idea is a bit too sloppy, or at least like we should really, I agree also, let's say, with the people who say that we should consider the method more carefully, and we should really like check whether or not there is real possibility or not. Okay. Thanks.